Hello, and welcome to Shine Sleep Stories. Tonight, we'll delve into a quiet, vast mystery. This mystery lies at the very edge of existence. There's a bizarre thought experiment that has preoccupied the minds of physicists, philosophers, and dreamers for almost a century. Imagine that the universe itself, not the stars or planets or galaxies within it, but the very content of existence is so vast that 2 points in the universe, though billions of light years apart, could actually touch each other. Not metaphorically, not approximately, but precisely, topologically, physically, somehow connected by a link that cannot be discovered by ordinary travel. This is the essence of the wormhole, an imaginary tunnel, a secret passage through space-time. This idea doesn't come from science fiction or fantasy, but from a serious and rigorous study of Einstein's equations of general relativity. These equations were recorded over a century ago, and human intellect has proven them to be among the most efficient and surprising equations available today. The universe has predicted the existence of black holes and the persistence of light, due to its depletion, all of which have since been confirmed. And within this mathematics lies the exciting possibility of particle-like particles. This essay is an attempt to seriously consider this possibility. It does not claim that wormholes exist, as there is no observational evidence of them, but it will examine how resilient they are, where they theoretically come from, what it takes for them to exist, and what they would mean if they actually existed, independently, autonomously, and cosmologically. The journey through modern physics must confront the deepest investigations, the parts of spacetime, the meaning of quantum entanglement, the structure of reality in Planck performance, and the strange relationship between information and geometry. The journey will be long. It must be, because the universe is not superficial, space is not empty, time is not simple, and the possibility of hidden tunnels separating the far corners of existence. Where a sleepless night and a clear mind can be hidden, is a value considered until it is noticed. So, to begin with, not wormholes, but a vast formation in the night sky, immediately noticeable and observable. The stars are scattered across a dark canvas, separated by such vast distances that even light, traveling at 299,792 kilometers per hour, takes years, time, or millennia to pass them. The scattered space between these stars appears as if it were nothingness, a formless, passive, extinguished, maddening realm where energy merely moves. This insight is understandable, but profoundly wrong. Space is not nothingness. It is not the absence of something, but the presence of something. In its planet, in its atom, beneath its photon, there is an invisible, continuous, and profound structure. We call this space-time. And understanding what space-time truly is, not as a metaphor, but as a physical entity, is the fundamental step in defining what wormholes are not merely science fiction. The modern understanding of spacetime begins with Albert Einstein's special theory of relativity, published in 1905, and finds its full expression in his general theory of relativity, published in 1915. Special relativity unifies space and time into a single four-dimensional entity. The fact that length and time measurements are not absolute is demonstrated by their dependence on motion. Two objects moving at different speeds are being observed. They cannot agree on how much time elapses between the two events and how long ago these events began in space, but they will always agree on a certain spatial distance and a detailed knowledge of temporal information. This is called the space-time interval. This was the first clue showing that space and time are not independent entities, but elements of a single fundamental reality. The universe does not have separate components of three-dimensional space and one-dimensional time. It has four-dimensional space-time, and these are interwoven in such a way that its width depends on its magnitude. General relativity went even further. It showed that time and space are not a rigid background against which events occur. It is a dynamic, flexible, and responsive environment. The presence of mass and energy causes space-time to curve. This curvature determines how matter and energy move. This interaction often summarized by the statement, matter informs space-time how to curve, and space-time informs matter how to move, forms the basis of gravitational physics. Asterisk. What does spacetime curvature mean? It becomes easier to visualize. Imagine a two-dimensional surface, like a flat piece of rubber. If you pull this surface over a bowling ball, the surface curves. Straight lines drawn on a curved surface are no longer generally straight, they curve and become circular. An entity trapped on that two-dimensional surface experiences this curvature as a kind of gravitational force, an apparent force pulling it towards the center of the curvature. Asterisk. In reality, the situation is four-dimensional and quite complex, but the fundamental principle remains the same. Large bodies, such as stars and planets, create depressions in the four-dimensional structure of spacetime. Other nearby bodies move along curved paths caused by these depressions. They are not being pulled by a hidden force. They are simply following the most natural and efficient paths within a curved geometry. These paths are called geodesics. This means that what we call gravity, at a deeper level, is not a force at all. It is the geometry of spacetime expressing itself through the movement of bodies. Einstein's genius lay in recognizing this, in understanding that a purely geometric description of a curved four-dimensional space could explain everything we observe as gravity. There is no hidden force, no mysterious effect at a distance, just geometry. Asterisk. When we accept that spacetime is a physical medium with real properties, curvature, cause and effect structure, topology, rather interesting set of phenomena can emerge. Spacetime can vibrate. When large objects accelerate, ripples occur in the structure of spacetime, creating waves that propagate at the speed of light. These are gravitational waves, first predicted by Einstein in 1916 and directly detected by the LIGO Observatory in September 2015. The detection of gravitational waves was one of the most spectacular confirmations in the history of science, proof not only of general relativity, but also of the existence of spacetime as a medium through which disturbances can actually travel. Asterisk. Spacetime is also the universe itself is expanding. Distant galaxies are moving, not because they are moving away from us, but because the space between us is growing. There is a subtle but important difference between moving through space and expanding space. The recession velocities of the most distant observable galaxies are derived from the redshift of their light and exceed the speed of light. This does not violate relativity, because these galaxies are not moving through space faster than the speed of light. Space itself is expanding, taking the galaxies with it. Asterisk. And spacetime is compressible. Near a black hole, the curvature of spacetime becomes so extreme that all geodesics are possible. Paths within geometry converge to a single point. Even light cannot escape. Time, as measured by a distant observer, appears frozen at the event horizon. The mathematics of general relativity loses its functionality at the point of collapse, suggesting that more than our current understanding quantum gravity is needed to explain what happens there. Asterisk. It is in these extreme conditions, around black holes and near the hypothetical beginnings of new universes, that the possibility of wormholes first emerges, because in the most radically curved regions of spacetime, geometry has the ability to do the most astonishing things. Before we begin to understand what, there's another concept that needs to be introduced, and that's one of physics' least appreciated ideas: topology. Topology is the branch of mathematics that doesn't deal with shape and distance measurement. It deals with a more fundamental question: how a space is connected. Two surfaces can have the same topology, even if their appearances are very different. A coffee cup and a donut are topologically identical. Both have a hole running right down the middle. One can continuously change shape with the other, without tearing or gluing. But neither can ever transform into a sphere, because a sphere has no hole. A sphere has a different topology. Now the critical question is, what is the topology of the universe? Most of us assume the universe is simply connected. That is, any loop in space can be continuously reduced to a point. This is the topology of a smooth, infinitely flat plane or a smooth sphere. But general relativity allows for the fabric of spacetime to bend in arbitrary ways, allowing for more exotic topologies as well. Space can be multi-connected. There can be topological arms, bridges, or tunnels that connect distant regions that appear quite separate from the outside. Wormhole is precisely such a topological feature. It's not a hole in space, nor is it a tear in the fabric of reality. It's an arm that provides a smooth, uninterrupted connection between two distant regions, made possible by how space-time bends and folds in higher dimensions. And the first serious hint that such structures might be permitted by the laws of physics came from a 90-year-old paper written by one of the greatest physicists of the 20th century. Asterisk. At the heart of general relativity lies a set of 10 equations. Einstein's field equations that describe the relationship between the curvature of spacetime and the distribution of matter and energy within it. Written in the simplified notation of tensor calculus, they appear quite simple. G_microν equals 8T _microν G and C are taken as 1 in natural units. On the left is the Einstein tensor G_microν, which provides information about the curvature of spacetime. On the right is the stress energy tensor T_microν, which carries information about the distribution of mass, energy, momentum, and pressure. Asterisk. This equation essentially states that the geometry of spacetime, its curvature, shape, and topologies determined by the entities within it. Conversely, the movement of those entities is also guided by this geometry. There is a deep relational picture of the universe. Space and matter are not separate entities, but a single coherent system that shapes each other. Asterisk. What makes this system complex and difficult to study is the nonlinearity of the equations. For example, in Newtonian gravity, the gravitational field of a group of masses appears only as the sum of the individual fields, whereas in general relativity, the curvatures created by different sources interact with each other in a complex way. The geometry formed when two large objects rotate each other is not the sum of the geometries each would create individually. This nonlinearity explains why exact solutions to Einstein's equations are so rare and valuable. The few solutions we have, Schwarzschild, Kerr, Rice, Friedman, Lemaitre-Roberson, Walker, are studied in depth. Asterisk. Given a specific spacetime, geometry a solution specific to Einstein's field equations, we can ask how objects move within that geometry. The answer emerges elegantly. Freely falling bodies follow paths that minimize, or more accurately, extremate the spacetime interval. In flat spacetime, these paths are straight lines. In curved spacetime, they become curved paths, representing the natural and unforced motion of the bodies. Asterisk. The Earth revolves around the Sun, not because of the gravity it exerts on it, but because of the geodesic it follows in spacetime, which is bent by the Sun's mass. From the Earth's own frame of reference, it appears to move along a straight line, the straightest line in a curved geometry. The path returns to itself, forming an orbit around the Sun. Asterisk. Light follows geodesics where the spacetime interval is 0. This is the geometric meaning of the statement that light always travels at a constant speed. It always passes through special curves of 0 length. Near a large object, these 0 geodesics curve. A photon passing by the Sun follows a curved 0 geodesica curvature first measured during the 1919 solar eclipse, providing the first experimental confirmation of general relativity. Asterisk. The concept of geodesics becomes even stranger and more profound near sources of extreme gravity. Near a black hole, geodesics spiral toward the event horizon. At the event horizon, 0 geodesics paths of light direct only inward. There are no 0 geodesics extending outward from the event horizon. This is the geometric meaning of the event horizon. It is a surface of irreversibility where all geodesics go toward the singularity and none go outward. Asterisk. When Einstein published his field equations in November 1915, he did not immediately find an exact solution. Finding solutions to nonlinear partial differential equations is quite difficult. But within a few months, Karl Schwarzschild, a German physicist and astronomer working on the Eastern Front of World War I, found the first exact solution. This describes the geometry of spacetime outside a spherically symmetric and non-rotating massaplanet. a star, or a non-rotating black hole. Asterisk, the Schwarzschild solution is remarkable in many ways, but one feature in particular stands out. It contains a singularity. When the Schwarzschild radius is r equals to gm per c squared, where g is Newton's gravitational constant, m is the mass of the object, and c is the speed of light, the metric tensor of the solution seems to explode. For years, physicists debated whether this singularity was physical, a real property of geometry, or merely a coordinate illusion. Asterisk, the result, developed over several decades by Eddington, Lemaitre, Kruskal, and Schicker, revealed that the Schwarzschild radius is not a geometric singularity, but an irreversible surface where all geodesics are oriented toward the singularity and none emerge outwards. And the strange appearance of this surface in the original coordinates was indeed a coordinate illusion. In the more refined coordinate system, the Kruskal-Schicker coordinates, the geometry of the Schwarzschild spacetime becomes completely clear. So, what does this clarified geometry reveal? Something unexpected and extraordinary. The most extended Schwarzschild solution describes not just one universe, but two, which converge at a central point in 1935. Albert Einstein and his collaborator Nathan Rosen published a paper that, while seemingly concerned with the mathematical structure of the Schwarzschild solution, actually contained an idea that would form the basis of one of the most interesting areas of theoretical physics. The paper was titled "The Particle Problem in General, Relativity," and its primary aim was to understand fundamental particles based on general relativity, not to define wormholes. Asterisk, Einstein and Rosen were concerned about singularities in general relativity. A singularity is a point where the curvature of spacetime becomes infinite, representing a fundamental breakdown of the theory. They believed that singularities could be avoided by altering the topology of spacetime. Their plan was to replace the singular point of a Schwarzschild black hole with a smooth bridge, connecting to separate regions of spacetime. Asterisk. They called this bridge the Einstein-Rosen bridge, but it later became known by the term wormhole, coined by physicist John Archibald Wheeler in 1957. Upon carefully examining the mathematics, they discovered that the Schwarzschild solution, when extended to its highest degree, instead of being cut off at the singularity naturally contained to separate outer universes, each with its own asymptotically flat regions of space, connected by a thin throat. Asterisk, this was the original wormhole, not a tunnel dug through space with some kind of exotic technology. It was a property inherent in Einstein's equations when applied to the geometry around a spherical mass. It appeared that hidden passages could exist within the universe, not added manually, but arising spontaneously from the geometry. Asterisk, to fully understand the Einstein-Rosen bridge, physicists developed a coordinate system that encompassed the entire extended Schwarzschild spacetime without coordinate singularities, the Kruskal-Schicker coordinates. In this coordinate system, all spacetime can be represented on a single diagram, and the cause and effect structure becomes fully understandable. Asterisk, the Kruskal-Schicker diagram shows 4 distinct regions. Region 1 is our universe, the outer spacetime we observe and live in, stretching from infinity to the event horizon. Region 2 is the interior of the black hole, the area bounded by the singularity at the top of the diagram, from which nothing can escape. Region 3 is the white hole, a time-reversed black hole, a place where only matter can exit, not enter. And Region 4 is a second outer universe, a complete mirror image of Region 1, connected to our universe by the throat of the wormhole. Asterisk. The Einstein-Rosen bridge is the link between Region 1 and Region 4. In terms of spacetime, the two outer universes are not truly separate. They are both parts of a single connected manifold, joined at the throat of the wormhole. A traveler in Region 1 and a traveler in Region 4 are, in a profound topological sense, in the same universe, just on opposite sides of a hidden bridge. Asterisk, but the Einstein-Rosen bridge has a profound problem. It is not traversable. This is not a limitation related to engineering or technology, but a fundamental consequence of geometry. The bridge exists, but only momentarily. The throat of a wormhole connects to outer regions in a single moment in time, and then closes immediately afterward. A singularity closes it. Any traveler or signal attempting to pass from one side to the other will inevitably collide with the singularity before reaching the other universe. Wormholes form and collapse faster than light can travel. The impassability of the Einstein-Rosen bridge was disappointing from a science fiction perspective. And from a physical standpoint, it raised a profound question. If natural wormholes in general relativity were impassable, were there other kinds of wormholes? Could the geometry of spacetime theoretically support a stable and passable link between distant regions? This question was seriously considered in 1988 by two physicists from the California Institute of Technology, Kip Thorne and Michael Morris. Their work was partly driven by science fiction writer Carl Sagan's desire to find out if there was a physically possible way for the main character in his novel, Contact, to travel between stars. Thorne and Morris did not dismiss this idea. With mathematical precision, they asked, what conditions must a passable wormhole satisfy? Their analyses provided a clear and striking answer. A passable wormhole can only exist if it contains exotic matter with negative energy density. This is not a trivial technical requirement. It is a profound and strange demand that lies at the frontier of our understanding of quantum physics. To understand why exotic matter is necessary, we need to understand the geometry of a traversable wormhole in more detail. This is one reason for Betelgeuse's pulsation. As the giant convection cells rise and fall, they cause the star's outer layers to move. When a particularly large cell comes to the surface and is pushed outward, the star brightens slightly. When it falls again, the star dims. The changes in Betelgeuse's brightness that astronomers have observed for centuries are partly due to the breathing of these giant cells. Second, winds. Betelgeuse is shedding its outer layers into space. All stars lose mass through stellar winds, which are streams of electrically charged particles that flow outward from their surfaces. Although the sun's solar wind is invisible, it is constant and measurable, spreading throughout the entire solar system. However, Betelgeuse's mass loss makes the sun's wind appear like a gentle breeze compared to a hurricane. Betelgeuse is perhaps losing hundreds of millions of times more mass than the sun. During its lifetime as a red supergiant, it has released enough matter to form several suns. This matter, mostly hydrogen and helium, but with heavier elements, too, now envelops the star in a massive irregular nebula. The layered atmosphere stretches hundreds of billions of kilometers in every direction. Using the most sensitive instruments, astronomers have mapped this matter and found that it is not uniform. There are clumps, arcs, and spiral structures, evidence of jets of matter ejected by the force of large convection cells emanating from the star's surface, captured and shaped into bizarre forms by the stellar wind. When Betelgeuse's wind collides with interstellar matter, the thin gas beyond the star's direct influence, it creates a wave of arrows. This appears as a slightly curved arc far ahead of the star in the direction it travels through the galaxy. Betelgeuse is moving through space. Like everything else, it orbits the center of the Milky Way, a huge, slow circle that takes hundreds of millions of years to complete. But it also moves relative to its local stellar neighborhoods. They believe Betelgeuse was born in a different region of the galaxy and traveled through space for millions of years to reach this point. Third, darkness. If you could somehow orbit Betelgeuse the way Earth orbits the Sun at the same proportional distance, receiving the same proportional energy, you would orbit it at a distance several times greater than Neptune's distance from the Sun. From that distance, Betelgeuse would fill the sky, not like the Sun fills the sky from Earth, as a very bright disk when viewed directly, but small enough to cover with your finger. No. Viewed from a proportional orbit, Betelgeuse would fill a significant portion of your entire field of vision. Looking in any direction near it, you would only see stars. Betelgeuse's light is also different from sunlight. The Sun emits most of its energy in visible light, but also produces significant amounts in ultraviolet and infrared light. Betelgeuse, because its surface is cooler, emits most of its energy in infrared light-long wavelengths invisible to the human eye. The visible light it emits is predominantly at the red end of the spectrum, which is why it appears orange-red to us. If you could see its infrared light, Betelgeuse would be even more spectacular. The star shines in infrared light. Fourth, age. Betelgeuse is approximately 8 to 10 million years old. That seems like a long time, almost 100 times longer than the entire history of the Homo species. But on a cosmic scale, it's like a blink of an eye. Our own sun is almost 5 times older. The universe itself is 14 billion years old. Despite all its immense power, despite the shocking energy it has released throughout its lifetime, Betelgeuse is a young star. A bright, careless, wasteful young star. It is consuming its legacy so quickly that it surprises even its more modest neighbors. And it is almost running out of fuel. Towards the end of 2019 and the beginning of 2020. An event occurred on Betelgeuse that thrilled the astronomy world and received rare attention from the general public. Betelgeuse dimmed. It dimmed dramatically. In February 2020, it dropped to its lowest brightness recorded in over a century of systematic observations. It lost its place among the 10 brightest stars in the sky and fell behind even the 20 brightest stars. Observers with keen eyes could tell that something was wrong. Orion's familiar orange shoulder, Betelgeuse, had faded. Many studies were published in the astronomy community. Theories were put forward and debated. Was this the beginning of the end? Was Betelgeuse preparing for an explosion? Had the instability following the core collapse finally begun? The answer, ultimately, was no, but the fact was almost as intriguing. The event was this. A massive convection cell on Betelgeuse's surface ejected a huge amount of matter. Billions of times more matter than a typical solar wind from our sun was ejected in a single event. This matter-hot plasma moved outward from the star's surface. As it moved away from the intense heat of the star's vicinity, it cooled. As it cooled, its molecules turned into dustiny solid particles made of carbon and silicate components. And this dust blocked the light. A newly formed dust cloud lay between Betelgeuse and Earth, obscuring a portion of the star's disk and causing the dramatic dimming that observers witnessed. Astronomers named this event the Last Great Dimming, and analyzers using multiple space telescopes have allowed them to reconstruct what happened in detail. Asterisk, the event was reminiscent of several things at once. First, Betelgeuse is a dynamic, active, and unstable star in its later life. Ultimately, the intensity of the eruption that led to the Great Dimming the energy required to eject. So much material with such force was enormous. The star wasn't just sitting quietly. Secondly, despite all the advanced tools of modern astronomy, we cannot precisely predict when Betelgeuse will explode, nor can we confirm that an explosion is imminent. In astronomical terms, imminent can mean anything from tomorrow to 100,000 years from now. The star's behavior gives us clues, but these clues are vague. Thirdly, people are deeply affected when they learn that a bright star nearby is about to explode. The Last Great Dimming made headlines worldwide. Photos of Orion circulated on social media with impressive captions. People who hadn't looked at the sky for years went out at night to check that famous shoulder of the hunter to find its familiar pattern. Something within us reacts to the stars. This has always been present in every era of human cultures. In all civilizations that have looked at the sky and tried to understand what they saw, stars are not important to us in a practical sense, because they are so far away and we cannot directly influence them. Yet we look at them. We give them names. We tell stories about them. We feel something when we learn that one is dying. This is not foolishness. Perhaps it is one of the most beautiful things about us. Asterisk, a thought worth pondering before falling asleep. The light from Betelgeuse that reaches your eyes right now, the pale red-orange glow you might find on Orion on a clear winter night, emanated from the star. Approximately 700 years ago, the Black Death was beginning its journey across Europe. In China, the final years of the Yuan dynasty were taking shape. In the Americas, great civilizations were being built. Trade was taking place, and complex astronomical traditions were being maintained. Dante Alighieri had recently finished the Divine Comedy. Ibn Battuta had begun his voyages around the known world. All these events were unfolding under the veil of light receding from the surface of Betelgeuse at the very moment your light reaches it. The star you see in the sky is not as it is now, but as it was in the past. An image from 700 years ago continues its journey to reach you. This is true for every star you have ever looked at. The night sky isn't a snapshot of the present, it presents a mosaic of different moments in the past. Each star displaying its appearance at a different time, depending on its distance. Some stars you see may be images from just a few years ago, others hundreds of years ago, and some tens of thousands of years ago. The Andromeda Galaxy, appearing as a faint speck of light when observed on a very dark night, shows what it was like 2.5 million years ago, before our species, before the emergence of humankind, before the last ice age, before the human brain as we know it. The sky is like a time machine. Whenever you look up, you're constantly glimpsing the past. Asterisk, this means something significant, especially in relation to Betelgeuse. It's theoretically possible, but it seems unlikely. Perhaps Betelgeuse has already exploded. Its iron core may have already collapsed. The supernova process may have already begun, and the light from that explosion may be traveling toward us right now, at the speed of light, but it will still be hundreds of years away. We have no idea about this. Here, in the quiet darkness, in a peaceful and familiar future, the wave of light, a calling, an immense flood of light and radiation, may be moving right now. It's not threatening. 700 light-years away, it's not dangerous. But it's coming. When Betelgeuse arrives, it will briefly be brighter than a full moon. It will be visible during the day. At night, it will cast shadows. For several weeks, it will be the brightest object in the sky after the sun. People will stand on sidewalks and point at it. Media outlets will interrupt their normal broadcasts. Children will ask their parents what the bright light is, and their parents will have to decide how to explain that a star has died, or maybe it hasn't happened yet. Maybe Betelgeuse is still there, continuing to burn, flicker, and shed its outer layers into the darkness. Maybe it will continue to do so for another 100,000 years. We don't know. We can't know. We can only watch, wait, and look at the sky with patient curiosity, which is always one of our best qualities. Let's imagine this. Now, let's imagine we're there at the moment the event occurs. We're not on Earth. We can't be there for this part. We're still here, in space, near Betelgeuse, floating in what we imagine an impossible safety. Let's observe. Asterisk, it all begins at the core. For days, the silicon at the core has been coalescing, forming iron. Iron accumulates. For a short time, an equilibrium is established. The energy from the silicon coalescence pushes outwards from the iron core, while gravity balances the inward pull. But the iron core grows. More and more iron is added to it with each passing second. The mass of the iron core increases toward a critical threshold. When the iron core reaches about 1.5 times the mass of the Sun, this value is known as the Chandrasekhar limit. An extraordinary event occurs. Asterisk, the core becomes unable to support itself. The electrons in the core were constantly exerting pressure. Electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. This provided resistance to compression, even when the temperature pressure was insufficient. However, once this mass is reached, even the electron degeneracy pressure becomes insufficient. Asterisk, in an instant within milliseconds, microseconds, the nucleus begins to collapse. Protons and electrons compress together, forming neutrons and neutrinos. The nucleus, roughly the size of Earth, transforms into a neutron ball about 20 kilometers in diameter. The density of this object is indescribable. A teaspoon of its material would weigh billions of tons on Earth. Gravity at the surface is so strong that the escape velocity approaches a significant fraction of the speed of light. Asterisk, as the nucleus collapses into this ultra-dense neutron state, it bounces back ejected outwards. Neutron matter has its own resistance to compression, and when collapsing matter strikes it, it bounces back outwards. A shockwave propagates outwards from the nucleus. Meanwhile, neutrinos countless, an almost inconceivable quantity formed during the collapse, are emitted outwards from the nucleus. Neutrinos interact with matter quite weakly. Under normal conditions, a neutrino would not stop while traveling through solid lead for a life. However, during the collapse, the outer layers are so dense that even neutrinos interact with them only slightly. The neutrino stream leaves only a tiny amount of energy in the falling matter. That tiny amount of energy is enough. The combined effect of the shockwave and the neutrino energy accumulation reverses the inward fall, pushing the star outwards. The star's outer layers, hydrogen, helium, carbon, oxygen, and heavier elements spread over hundreds of millions of kilometers, are pushed outwards. This explosion is called a core collapse supernova. The energy released during the core collapse, just the core, in just those few milliseconds, is roughly equivalent to the total energy our Sun emits over its 10 billion year lifespan, and a large portion of this energy is transmitted via neutrinos, the light of the explosion, the enormous flare that makes Betelgeuse visible from Earth during the day represents only about 1% of the total energy released. The shockwave ejects from the star's interior at a fraction of the speed of light. Layer by layer, it reaches the star's outer shells and tears them apart. The star disintegrates from the inside out. The matter accumulated in the layers outside the core, helium, carbon, oxygen, neon, silicon, and iron, all like layers of onion, is ejected into space. At the temperatures generated by the explosion, nuclear reactions produce elements heavier than iron elements that cannot be created by normal fusion processes within stars. Gold is formed, platinum, uranium, lead. The heavy elements of the periodic table, these make up your jewelry. The weights on car wheels, the fuel rods in nuclear power plants, are created in the force of supernova explosions and scattered throughout the galaxy. The eruption expands. The shockwave spreads through the vast cloud of matter that Betelgeuse has emitted over hundreds of thousands of years. It licks at that matter, ionizing it and causing it to glow. What was once a faint diffuse cloud of gas around a dying star becomes a bright, expanding shell of plasma supernova remnant. Over the centuries, this remnant will expand, cool, and thin out, eventually becoming a very faint cloud of gas, barely distinguishable from the background. The iron core, at the center now, a neutron star, or, if the original star was large enough, a black hole, will simply spin in the space where Betelgeuse once shone. And the light from all of this will reach Earth. It will manifest itself as a glow in the sky. Perhaps it will appear as a new star out of nowhere, because, depending on the stage of the explosion and the amount of dust in its path, the first wave of light may arrive before astronomers receive any further warning. Or, it may arrive as Earth's neutrino detectors, large buried water tanks originally designed to detect rare neutrinos from the Sun, capture the flood of neutrinos from the core collapse, traveling at near light speed and interacting only weakly with the matter they pass through. These neutrinos arrive on Earth hours before visible light. The detectors will sound the alarm. Astronomers will be notified. For several hours they will watch the sky anxiously, knowing what is coming, their instruments ready, and then the light will come. After a supernova, the universe moves on. It always does. Betelgeuse's neutron star, with its core remaining in place, is a unique object. It's about 20 kilometers in diameter, close to the size of a large city on Earth. It contains 1.5 times the mass of our Sun. It's so dense that a single cubic centimeter of its matter weighs about 100 million tons. It's spinning. As the core collapsed, it retained the angular momentum of the larger star. Just as a figure skater spins faster when they pull their arms inward, the collapse from something the size of Earth to the size of a city reaches incredible cyclical speeds. Newly formed neutron stars can spin hundreds of times per second. As they continue to spin, if the magnetic field is correctly oriented, neutron stars emit beams of electromagnetic radiation from their poles, like a cosmic lighthouse. If Earth is in the path of these beams, we can detect it as a regular rhythm of radio waves or X-ray waves. This type of object is called a pulsar. The most famous pulsar we know is at the center of the Crab Nebula, a supernova remnant observed from Earth in 1054. Chinese astronomers recorded it. Arab astronomers also recorded it. For 23 days it was visible even during the day. The nebula it left behind is still expanding today, a beautiful, shimmering tangle of gas threads that we can see with a modest telescope. And at its center, there is a small neutron star that still rotates 30 times every second. This is the future of not its glowing daytime visibility, not a spectacular few weeks of light show. These are the opening moments of a story that will last for tens of thousands of years. The nebula, fading, slowly dispersing into the interstellar medium, and in the midst of it, there is something impossibly dense, impossibly fast-spinning, impossibly strange. But let's not forget the other legacy. The matter ejected during the supernova, all that hydrogen, helium, carbon, oxygen, iron, gold, and uranium will join the interstellar medium. It will drift and disperse for millions of years. Perhaps it will eventually reach a molecular cloud. That cloud may then collapse and give rise to new stars. These stars may have planets. Somewhere on those planets, the raw materials necessary for the chemistry that forms the basis of life can be found: heavy elements, carbon, oxygen, nitrogen, iron, phosphorus, calcium, potassium, and sulfur. This isn't an analogy or a fancy phrase. That's just how it works. The carbon atoms in your body didn't form in the Big Bang. Hydrogen formed, helium formed, but carbon is necessary inside a star. The iron in your blood doesn't come from just a star, but from the excrement of a supernova explosion. You are, quite concretely and measurably, made of the remnants of stars that exploded long before our sun. When Betelgeuse explodes, it will scatter the products of its long life into a local region of the galaxy. And billions of years later, somewhere, there's a chance these materials will become part of a planet. They could be part of an ocean. They could belong to a creature gazing at the sky and questioning the stars. We won't see it there. But this process continues uninterrupted. It existed before us. It will continue after us. We are a part of it. Dear Sir, Madam, as we slowly make our way home, it is important to take a few minutes to consider the concept of time. The human mind is not designed to comprehend the timescales required for the evolution of stars. We think in terms of hours, days, years, and generations. A human lifespan 70, 80, perhaps even 100 years is a length of time that we often struggle to grasp. History, stretching back to the 5,000 years ago, when the first writing systems appeared, is quite difficult to concretize. There is another perspective on the paradoxes of time travel. Different from Hawking's time conservation theory, this is the principle of self-consistency. Developed by Igor Novikov, and also called Novikov's self-consistency hypothesis. According to this principle, the universe does not forbid time travel, but imposes limitations on it. Every event occurring in a time travel loop must be It is impossible for a time traveler to go back in time and kill their grandfather, because if they did, they could not have gone back in time, and therefore their grandfather would not have died. According to this perspective, the only time travel loops that can exist are those where the past is consistent with its own future. This may seem restrictive, but it actually opens up many interesting possibilities. A traveler could go back in time and have a conversation with their younger self, provided that this conversation is consistent with what the younger self remembers. A time traveler could give the past information that was not produced from anywhere. This information only exists in a self-consistency loop and has no original source. This is the bootstrap paradox, and while logically consistent, it is philosophically unsettling. The principle of self-consistency is mathematically defined with precision. In the formulation of quantum mechanics concerning quantum fields on curved spacetime, this principle is naturally applied. The quantum state of a system on a spacetime with closed time-like curves must be consistent with the evolution of that system along the closed time-like curve. The solutions to the equations of motion are automatically self-consistent. meaning that paradoxical histories are automatically excluded. Chapter 8. Could wormholes have already existed? Everything we have discussed so far has focused on the theoretical properties of wormholes and the conditions required for their existence. However, a natural and urgent question arises. Could wormholes have formed naturally throughout the history of the universe without any engineering? If so, do some still exist today? The most natural environment for the formation of wormholes is the very early period of the universe. During the Planck epoch, particularly the first y-43 seconds after the Big Bang, the universe's temperature and energy density were so extreme that quantum gravitational effects became dominant. It is thought that the topology of spacetime was likely not stable during this period. Spacetime bubbles violent. Quantum fluctuations in the geometry of space at the Planck scalar for changes in the topology of space. Wormholes may have formed, evolved, and either stabilized or dissolved. If any wormholes formed during the Planck epoch survived and grew with the expansion of the universe, they may still exist today, perhaps on macroscopic or cosmic scales. This scenario is speculative, as we lack a quantum gravity theory that can reliably calculate the probability of wormhole formation in the early universe. However, it is certainly not impossible. The universe has existed for 13.8 billion years. Its topological structure in its earliest moments may have been very different from what we observe now. Another potential formation mechanism involves protozoal black holes. In the very early universe, density fluctuations could have created regions dense enough to form black holes. As we discussed in the context of the Schwarzschild solution, maximized black hole geometries naturally include wormhole structures. If primordial black holes did form, and Penrose diagrams represent real physical entities, then wormhole-like structures might be associated with these black holes. However, of course, the uncrossable nature of the Einstein-Rosen bridge means that these wouldn't be useful shortcuts, but rather topologically non-trivial features of the universe. Research explores whether wormholes can spontaneously create themselves through quantum processes without the extreme conditions of the early universe. This work is carried out over path integrals in time and space geometries, over topologically complex structures including wormholes. In this context, wormholes emerge as chairpoints of Euclidean gravitational action. While these structures are not solutions to the classical equations of motion, they make significant contributions to the quantum mechanical probability amplitude for a given process. They are sometimes called virtual wormholes or quantum wormholes, a term similar to virtual particles in quantum field theory. The significance of these virtual wormholes has been a subject of debate. In the 1980s and 1990s, Stephen Hawking, Sidney Coleman, and other physicists investigated whether the sum of all topologies, including wormhole topologies, in the Euclidean path integral could explain some properties of low-energy physics, such as the cosmological constant. These calculations have yielded interesting but controversial results, and the technical challenges involved in defining and calculating the path integral over topologically complex spacetimes are considerable. 8.3 Wormholes and black hole evaporation in context. One of the most active areas of research on wormholes today is their role in the quantum mechanics of black holes, particularly the information paradox. When a black hole forms from matter during collapse and evaporates via Hawking radiation, what happens to the information present in the original matter? Hawking radiation is first and foremost thermal. It does not contain information about a particular arrangement of the matter that formed the black hole. If the radiation is purely thermal during the evaporation process, the information is irreversibly lost when the black hole eventually disappears. This is a fundamental principle of quantum mechanics. Information must always be conserved in quantum evolution. This is the black hole information paradox, and it has been one of the major puzzles of theoretical physics for decades. Recent studies, particularly the discovery of the Page curve in the context of Jackie-Teitelbaum gravity and related models, suggest that unity is conserved, that information is ultimately recovered in Hawking radiation. How this happens is critically related to the chairpoints found in the gravitational path integral with a wormhole topology. Specifically, a structure called a replica wormhole, which connects different spacetime replicas in a path integral calculation, appears to be responsible for the correct late-time behavior of Hawking radiation that ensures unity conservation. This is a striking result. Even virtual and quantum mechanical ones play a vital role in the coherence of black hole quantum mechanics. Their topological contribution to the path integral is not an unusual fix, but a physically necessary component. If this view is correct, then wormholes are not a speculative embellishment on standard physics, but are integrated into the foundations of quantum gravity. One of the most frustrating aspects of global wormhole physics is how difficult it is to distinguish a wormhole from other celestial objects using current observational methods. From a distance, the mouth of a wormhole, that is, its entry point, will look very similar to a black hole. It will have a strong gravitational pull, deflect light, and, depending on its properties, may be an accretion disk with material falling into it. However, the key difference is that a wormhole mouth does not have an event horizon. Light and matter approaching the mouth will exit on the other side instead of being trapped inside. But how can a distant observer tell whether a compact and heavy object has an event horizon or a wormhole throat? This is a complex question, and the answer depends on the specifics of the observation. One approach is to study the behavior of light around the object. A black hole bends light into a circular orbit, creating a characteristic shadow in its photon sphere with a radius of 1.5. This surrounds a dark region enclosed by a bright ring of light with gravity lensing. A wormhole produces similar effects, but the specific shape and brightness of the photon ring may vary. With detectable differences, gravitational lensing, the bending of light by gravity, is one of the most effective methods in observational astronomy. A passable wormhole creates a characteristic lensing pattern different from that of a black hole or neutron star. Specifically, a wormhole can form the classic Einstein ring seen around light reflecting off the object, and additional images formed by light passing through the wormhole and exiting on the other side. Theoretical calculations regarding wormhole lensing have been performed by a number of groups. These results suggest that the features of a wormhole's photosphere and shadow may be distinguishable, at least theoretically, from observations of a Kerr black hole. The Event Horizon Telescope, which in 2019 produced the first direct images of the shadow of a black hole at the center of the M87 galaxy and subsequently captured the shadow of Sagittarius A** at the center of our Milky Way galaxy, has sufficient resolution to distinguish some wormhole geometries from black holes. However, these differences are subtle and depend on a specific wormhole metric, which is not uniquely determined by theory. A dedicated observation campaign targeting compact objects with unusual signs of gravitational lensing could theoretically detect a wormhole. However, this requires the existence of a sufficiently large wormhole in the observable universe and the ability to model its lensing signature accurately enough to distinguish it from other explanations. If a wormhole's mouth is located in a region where matter can accumulate, for example, in the center of a galaxy where gas and dust are abundant, an accretion disk forms. The characteristics of this disk and the radiation it emits can, in principle, distinguish a wormhole from a black hole. The main difference is that the matter falling into the wormhole is not permanently trapped. That matter passes through the throat and emerges on the other side, possibly in a very different environment. This means that the energy released as a result of the accretion can be different from that of a standard black hole. In particular, the absence of the most stable circular orbit inside the event horizon, characteristic of black holes, can affect the temperature and brightness of the accretion disk in measurable ways. Some researchers have suggested that mysterious signals, such as millisecond radio bursts detected from distant sources, can be explained by the idea is that a plasma stream passing through a wormhole could produce its own unique electromagnetic signature. This is a highly speculative idea, and there are other plausible explanations for fast radio bursts. However, This demonstrates the creative observational thinking required to investigate wormholes, in addition to electromagnetic observations, neutrino astronomy, and gravitational wave astronomy offer potential opportunities to understand the behavior of compact objects that could help identify wormholes. Neutrinos interact only weakly with matter and can pass through dense regions that light cannot. If there is matter falling around a wormhole, neutrinos originating from that matter may carry information about the wormhole geometry that photons cannot. Gravitational waves from a binary system that is a wormhole will transmit information about its properties in the waveform. The fluctuation produced after merger, the oscillating, diminishing gravitational wave signal, is particularly sensitive to the nature of the compact object. A wormhole has its own unique modes that oscillate when it decays, and these are different from the modes of black holes. Future gravitational wave detection instruments, including the planned LISA space-based detector and the Einstein telescope ground-based detector, will be able to achieve measurements with sufficient sensitivity to distinguish wormholes from black holes in specific scenarios. Science is not just a collection of information and equations, it is a way of understanding the world, and the deepest scientific ideas inevitably carry philosophical implications that immediately transcend their technical content. Wormholes are no exception. The possibility that two distant points in space could secretly be neighbors, the existence of hidden connections invisible from the outside, but real from the inside, raises profound questions about the nature of space, distance, and connection. We experience space as a geometric measure. The distance between two objects is something measurable, independent of our feelings towards those objects, their similarities, or their internal structure. The distance between two stars is the distance between them, no more, no less. A wormhole challenges this image. If a wormhole connects to distant stars, is the distance between them truly the apparent distance, or is it the wormhole distance the length of the tunnel? There is no definitive answer to this question, because distance is not an intrinsic property of spacetime. It depends on the path being measured. In a spacetime containing a wormhole, there are at least two natural paths between 2 points, connected by the wormhole, the outer path by going around the outside, through the surrounding space, and the inner path by going through the wormhole. These paths have different lengths. There is no certainty as to which represents the true distance. Both are real properties of geometry. Many profound philosophical issues are raised, particularly by wormholes, which are traversable and can be used as time machines. These wormholes create challenges in terms of our concept of cause and effect. In everyday life, causes always precede effects. This is not merely a psychological tendency, it is also embedded in the cause and effect structure of spacetime. In special relativity, the cone of light at each point divides events into those that occurred in the past, shaping the present, future events, those that may be influenced by the present, and those that occurred elsewhere, those not causally connected to the present. Closed time-like curves violate this structure of spacetime. Someone traveling through a closed time-like curve could in principle be both the cause and the effect of their own existence. They could send information into the past that influenced the decision to time travel. The logical consistency of such loops, the principle of self-consistency, may be maintained, but the philosophical landscape they present is quite disturbing. Some philosophers, in response to this challenge, have argued that our conception of cause and effect is too narrow, that it is based on the particular cause and defect order of the space-time structure we possess, not a fundamental logical necessity. If the universe allows for closed time-like curves, then cause and effect is not a universal law of nature in the universe, but a local approximation, valid in our space-time region, but not in every region. This leads to a philosophical conclusion that can be accepted depending on how committed you are to the idea that causes must always precede effects. Wormholes raise particularly interesting questions in the context of multiverse theories. Several independent streams of thought in modern cosmology: infinite inflation, the string view, the quantum mechanical interpretation of the multiverse, suggests that our observed universe may be one of many universes contained within a much larger structure, often called the multiverse. In most designs, the different universes within the multiverse are causally unconnected. No signals, matter, or information can pass from one universe to another. Asterisk, however, if wormholes suitable for passage could connect not just distant regions of the same universe, but entirely different universes, a scenario suggested by the maximally extended Schwarzschild spacetime structure, then it could mean the multiverse isn't as disconnected as commonly assumed. Wormholes could bridge otherwise isolated universes, allowing for the exchange of matter, energy, and information. Asterisk, this would have profound implications for the physics of the multiverse. It would show that different universes are not truly independent, but connected to a larger structure, and that their physical constants and histories are potentially correlated through wormhole interactions. It would also raise the possibility of a traveler leaving one universe via a wormhole and emerging in a universe where different physical laws, particle masses, and potentially different dimensions of space and time prevail, a scenario extremely bizarre, even for physicists. The ER=EPR hypothesis, as discussed in Chapter 6, raises a profound ontological question. What is spacetime at its most fundamental level? If spacetime geometry arises from quantum entanglement, that is, if spatial relationships between objects are encoded and determined by quantum interconnections, then spacetime becomes an evolving construct, not a primordial matter. This represents a significant shift in our understanding of what the universe looks like. Time and space would not be a pre-existing background against which matter and energy exist and evolve. Time and space would themselves be products of quantum interconnections between more fundamental degrees of freedom. The universe would not be a sum of objects in space, but a sum of quantum systems, and what we call space would be the geometric expression of the entanglement pattern between these systems. Asterisk, some proponents of this viewpoint, using the phrase derived from the qubit, argue that the classical world, including spacetime geometry, emerged based on quantum information. In this context, wormholes are not mysterious tunnels passing through a previous fabric. They are geometric expressions of strong quantum relationships. They are as natural and inevitable as those relationships themselves. At its deepest level, the universe may resemble a quantum network more than a three-dimensional solid, and wormholes may be the main pathways of this network, bringing nodes that are geographically distant from each other in the resulting geometry directly connected in the fundamental quantum structure. In this article, we've taken a long journey, from the smooth and continuous spacetime of classical general relativity to the bubbly and wavy quantum spacetime of Planck-scale physics. From the Einstein-Rosen bridge of 1935 to the ER=EPR hypothesis of 2013, from the theoretical requirements for a traversable wormhole to the practical difficulties of detecting one with our telescopes. It was a long journey, and like all long journeys into unfamiliar territory, it left us with more questions. The question that prompted us to embark on this journey, does space itself harbor hidden tunnels connecting distant galaxies, remains unanswered. We don't know if traversable wormholes exist. We don't know if the structure of the universe is simple and interconnected, or complex and highly interconnected. We're also not sure if the ER=EPR hypothesis is correct. We don't have a quantum gravity theory that can reliably calculate the probability of wormholes forming in the early universe or their stability against quantum fluctuations. Asterisk. However, we have learned a great deal about the nature of the problem. We know that wormholes are not forbidden by the known laws of physics. We know that general relativity, our best theory of gravity, inherently contains wormhole solutions. And we know that maximally extended Schwarzschild geometry connects to universes via a bridge. We know that traversable wormholes require extraordinary matter, and that extraordinary matter is not forbidden in terms of quantum mechanics, but that its production in large quantities is quite difficult. We know that virtual wormholes play a role in the coherence of black hole quantum mechanics, and we have an impressive hypothesis, supported by significant theoretical evidence, that wormholes and quantum entanglement are two aspects of the same phenomenon. Perhaps the most important thing we've learned is how ignorant we are about the structure of spacetime. The fabric of reality, which is quite familiar at the scales we inhabit and so well described by the equations of general relativity and quantum field theory, becomes a mystery at the Planck scale. We don't know what spacetime is made of, just as we don't know that it's made of molecules of water. We have no idea how spacetime arises from something more fundamental. We don't know what the true structure of the universe is, whether it changes, or whether what we call the universe is connected to other regions by hidden geometric bridges. These aren't just technical questions requiring patient calculations. These are questions about the nature of reality, how space is connected, whether the universe we observe is the complete story or just a local part of something much larger and stranger, whether the distance between 2 points is a fundamental or a derived quantity. These questions motivated the greatest physicists of the last century and continue to be the motivations driving the field forward today. Meanwhile, we have to accept the universe as it is: vast, curved, expanding, and filled with objects of complex geometry. The Event Horizon Telescope, by looking at the centers of galaxies, attempts to read the shape of the gravitational shadow cast on the light around compact bodies. Gravitational wave detectors, by listening to the vibrations of merging compact bodies, try to figure out at what specific frequencies spacetime vibrates when disturbed. Particle accelerators are examining the structure of matter at increasingly smaller scales, searching for extra dimensions or supersymmetric partners, and theoretical physicists, with increasingly powerful mathematical tools, are scrutinizing the equations of general relativity and quantum mechanics to find clues to a deeper structure. In the next few decades, one of these paths may bring us a surprise, an observation, a calculation, or a theoretical insight that changes our understanding of the structure of spacetime. It may turn out that the universe we live in is highly interconnected, secretly linked by bridges and tunnels we haven't yet discovered. It's also possible that the quantum vacuum is full of virtual wormholes, weaving the fabric of spacetime with entanglement at every point. It's also possible that the first hints of wormholes will come not from telescopes pointed at the sky, but from quantum information theory equations. As the Welles EPR assumption evolves into a complete quantum theory of gravity, and we're nearing the end, now it's time to relax and have a good night's sleep. You're about to drift off to sleep in an endless state of relaxation. Good night, sweet dreams.